Thank you. Okay, so today we're doing refraction. Last week we did reflection, today is refraction. And what refraction is when a wave enters a new medium at an angle, so it's not coming in straight in. At 90 degrees, it's coming in at an angle. It will turn. It changes its direction. And this happens because one side of the wave slows down first, and the other side of the wave does not. You can see this with this lawnmower example. On the sidewalk, it's going at one speed, but then this wheel hits the grass and slows down, and this wheel's still going the same speed. That makes the whole lawnmower turn. Works the same way when you're going the other way. This wheel speeds up first. That wheel's still going slower. It turns. Light and other waves do exactly the same process when they go from one medium to the next. Ocean waves do it when they go from deep to shallow water. And light waves do it when they go from air to glass or air to water, water to glass, etc. We're going to see a bunch of different examples of this in this PowerPoint in a second. To help you understand this, we often show waves as a series of wave fronts, these lines, that are all the waves next to each other with the same crests at the same points and the same troughs at the same points. So we call them a wave front. And so you can see it bending when it hits the surface. Much more easily that way. Okay, so any questions on refraction? Before I move on. Okay, so let's see some examples. Now sound, of course, being a wave, refracts. And it refracts we usually see this through hot and cold air. Sound travels faster in hot air or cold air. Connor, where does sound travel faster? Hot air or cold air? It's not cold air. Thanks for the guess. Zach?
Hot air, because the particles are closely condensed.
Because they're moving faster and they hit each other more often. So sound moves faster in hot air and slower in cold air. Good. So what happens is sound bends away from the ground. On a hot day, the air near the ground is hot, higher up is cold, so the sound will bend upward, away from the ground. This is why on a hot day, if you're standing next to each other or far apart, it's hard to hear the other person, because their sound waves are going up into the atmosphere. On a cold day, you get the reverse. The air on the ground is cooler, higher up is warmer, so the sound actually arcs back down. That's why you can hear stuff further on a cold day. Because it goes up, hits the warm air, arcs back down because of this curving. Refraction.
Then why is it so hard to talk to someone? When you're in the snow and you're farther from each other, how is it harder to talk to them?
In the snow, what you do is you need to speak up, because if you're speaking across, what happens is the snow acts as a sound baffler. The sound waves hit the snow. But if you speak upwards, it will arc. This works at night too. This is often at night next to a body of water. Water holds heat in, so and doesn't heat up as fast because of its specific heat. So it gets cool at night. It's warmer above it, so you can arc the sound waves across water. That's why when you're at lakes and stuff, you can hear people talking at campsites further away. It's because the sound is arcing across the water like that because of refraction. So anyways, sound refracts. But we're going to be talking more about light refraction. As light passes from one medium to another, it of course refracts. You can see it with this pencil. Is that pencil actually bent?
No.
No. That pencil is normal, but you can see it looks bent. And that's because of refraction. The light that we're seeing, as it hits the water, it bends. As it comes back out, it bends. So it looks like the pencil itself is bent. Prisms work through refraction. The light from the air hits the prism. It slows down. Because the prism is at an angle, it slows down at different areas. That's what splits out the colors. Each color slows down at a different speed. red slows down more, blue slows down less, and you split them all out between. This happens with glass and bottles and cups. Check out this glass. You ever see glass like this? It looks full, right? They put it in water. This is actually how full it is. The glass is that thick. Because glass and water have very similar index of refraction, so they refract almost the same, so you can see the actual thickness of the glass. And that's how it is above, too. It's just the going from the air to the glass bends it so much that it looks much fuller. They do this in lots of bottles, ketchup and stuff. Look, the bottle looks way fuller than it actually is because of the light refracting to the glass in the air. So, but yes, the light will refract as it goes through, creating this effect. It's one way companies cheat people a lot. Because that glass is not useful. Now, atmosphere will refract. We talked a little bit about this with sound, but it also refracts light. This is what causes mirages. You've seen mirages like this. Tyler, is this ground wet? What do you think? Do you think this ground is wet? I'm pointing it. What do you think? Just say yes or no.
Yes.
Yeah, it looks wet, doesn't it?
It's a mirage.
It's not, though. This is a desert. This is really dry, but it looks wet. So what's happening is hot days, the air right above the ground is hotter, and it gets cooler above it. The light, as it goes through the hot air from the cool air to the hot air, starts to bend. And it's multiple layers where it goes hot, hotter, 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 and so it bends more and more and more until it can actually bend all the way back up. So what you're seeing is the light like this, so you see like a reflection. Well, your brain reads that light only moves in straight lines. So your brain says that's a reflection. And what causes reflection? Water. So your brain says that must be water. So your brain does a lot of stuff where it takes shortcuts for you to help you out. So because the light is moving in a curved line, even though our brain doesn't think light moving in curved lines, it reads it as if it was hitting and then bouncing off like water. That's what causes mirages. This is also what happens at sunset. The sun seems really big and orange right at sunset. It's because it's not actually in our field of vision. The sun is actually underneath where we're looking, but the atmosphere refracts it so that we can see it. So it appears to be above where it is. It's actually not in a straight line path to us anymore. It's just a refraction effect. So when the sun goes down, you can actually see it for a couple minutes after it goes down because the atmosphere refracts it back to us. Questions on this? So I think I have one or two more slides.
Is that why it looks so much bigger too?
Yes, it looks much bigger because of the refraction effect. Yes. It looks much bigger and kind of oranger. Why does it look orange? We talked about that last.
That's why. That's why.
The longer for the light to hit you, it's going to change color.
Close. Why does it look orange?
And why is
It's
the
sunset. Yeah, why is sunset orange or red?
Oh, because oh, I have that.
I'm thinking through my notes right now.
The surface of the Earth, the atmosphere is thicker, and so red light and orange light
Yeah.
split off.
The word starts with C. S. Sorry. Scattered.
Yeah.
Okay, the red light gets scattered, not just the blue light going through the thin atmosphere, thick atmosphere. The red gets scattered as well, so we see red. Okay. Anyways, rainbow. How does a rainbow work? A rainbow works. Each raindrop acts like a very small prism for the rain. The light comes in, the white light comes in, and it refracts through the drop. Actually hits the back and reflects back out towards us because of the angle. The red light doesn't refract as much. The purple light refracts a little bit more. Red's about 42 degrees. Or, yeah, 42, and the blue's 40. So it's about 2 degree difference. And what you're actually seeing is you're seeing two different droplets. You're seeing the red from this one, because the red's on bottom. That's why it's on top. And you're seeing the purple from this one. That's why it's on bottom. So rainbows are actually seeing multiple droplets refracting light all at the same time. But it's all based on these angles. You have to be at the exact right angle to see it. Each water drop is a very small prism for the sunlight coming in. Let's do one more here. Total internal reflection. Now, one of the properties of refraction is that if you reach a certain angle, we call it the critical angle, it's different for all materials, the light no longer gets out at all. It refracts within the object. You can see that here with the laser beam. Fires in, and it comes back out this way. This is called total internal reflection. This is normal refraction. This is at the critical angle. It just refracts right along the surface. And if you go higher than the critical angle, it comes back into its own material. Different materials have different angles. Glass about 43 degrees. Water is about 48 to reach this total internal refraction. Diamonds actually have the smallest critical angle of any known material, 24.6 degrees. This is why diamonds shine, because when the light hits them, it bounces all the way around and comes back out. In fact, it comes back out and splits like a prism. This is also why we cut them in that exact shape. Because if you cut them in different shapes, what happens is the light refracts and gets out when it hits the other edges. But since we know the exact angle, we can know the best shapes to cut them in for light to make them sparkle the best. Modern technology is based around this total internal refraction. We build what's called fiber optics, like this. You may have seen those weird, they look like plastic tubes and lights go through them, and you can bend them and stuff. Those are primitive fiber optics, but basically they use a material, and they know it's refraction. What happens is the light bounces back and forth because of this total internal reflection. And so you can bend it and do whatever you want with it, and it just bounces around. So you can send information in the form of light through it at very fast speeds. Yeah.
Does it matter what angle you bend it at? Will it always change?
Yeah. Because it's designed. The thickness is the correct thickness. That it will always hit that total internal reflection angle. If it's thinner, it will stop. If you break it, the light will stop, and so on. Yeah.
So diamonds, if they look like they're not as clear, like they don't shine as much, is that because they're actually lower quality, or is it just because they're cut?
There's two reasons. Could be because they were cut badly. They didn't hit the right angles on the cuts, and so it doesn't sparkle. Or it could be an inconsistency in the material of the diamond, and then it doesn't have the same critical angle if it has impurities, and so that can affect it too. Jewelers are trained to tell the difference. Okay, anything else, guys?
Or they can just be really good. Yes.
That's true too. Anything else? Okay. Well, let's move on to our work this week.